Okay, good evening. So what we are going to do now is we are going to be doing a review of the beginning of calculus. And so hopefully we will have a number of these. This is going to be the beginning. It will cover through some things about limits. We won't quite get as far as continuity though. So the goal of this is that this is for CHE 7100. What I'm going to be presenting here is single variable calculus review. And this is part one, as I noted, hoping that we'll have a number of parts so that we can get everyone on the same page with regard to where we're at with mathematics. So even though I'm going to call this a review, there are some things in it that I'm going to focus on that are likely different from how you traditionally thought as an undergraduate. And that is, of course, on purpose, because this is a graduate level class. And what I want to do is highlight things in this of information that do pertain more to how we think at the graduate level about mathematics than how we think at the undergraduate level. And hopefully at the same time, I'm reminding you of things that you already do know from the undergraduate level so that bugs your mind, and that if there is something where you're like, oh, I completely forgot that, but then you do have the opportunity, of course, to go look into it, look it up, and make sure that you bring it back. So the book that I'm using for this is called Calculus 5th Edition. By James Stewart. I'm going to copy verbatim a lot of things from this. So that's the book I'm using. And so something that I think is very insightful that's presented in this book at the very beginning is that it says calculus is concerned with change, motion, and quantities that approach other quantities. I think that that's a very helpful guideline of what calculus is about. And so with that, we're going to start back at chapter 1. A lot of the things in chapter 1 are a super review in terms of that they're probably things that you feel like you've known for years, or that maybe even you feel are intuitive because they're things about functions and models. But I think we should not even take such things for granted, because I think that the older, more mature that we get, the more that we can start to understand some of the depth of mathematics that maybe the first time we learned it, say you were in high school or something like that, maybe you would have kind of glossed over it and said like, oh, the teacher says. That was at least true for me. I don't know if that's true for everybody, but hopefully now that we're going over it again, you might see it in a different way that just you never saw it before and be like, oh, I'm starting to better understand the depth of mathematics, what mathematics really is and what it's like. And so according to this book again, what is stated is that the fundamental objects that we deal with in calculus are functions. It's also something very important to note is that in calculus, we are going to be focusing on functions. So that means that things that cannot or are not described as functions would be a little more difficult to work with without some extension. So the first thing to understand is what is a function, since these are what we're going to be basing things off of. So this is just a definition, but it's the definition of what a function is. So a function f is a rule that assigns to each element in, x in a set A exactly one element called f of x in a set B. And so often we consider that A and B are comprised of real numbers. So we would write something like A is a subset or is equivalent to all of the reals, and same thing for B. So it's either a subset of, or it could also be actually fully the set of the reals. And so Set A is what we call the domain of a function. When we write a number as f of x, it is the value of f at x. The range of f is the set of possible values of f of x as x varies throughout its domain. And so the independent variables are going to be numbers that are in the domain of f, or it's going to be a symbol representing a number from that domain. And then a symbol that represents a number in the range is the dependent variable. And so often we can visualize functions of a single variable via their graphs. So the graph is going to be the set of ordered pairs x, f of x, such that x is contained in A. Now, the reason I wrote that, even though everyone probably knows what a graph is for a function of a single variable, is that this is introducing some notation that I think is important. So this line here means such that, this means is contained in the set, things like that. So there are several ways that you can represent a function. So either you can write it in words, you like something along the lines of, this depends on that in such and such a way. You can write them by a table of values. You can make a graph of a function and say, that's the function. You can also write out the function with an explicit formula if that's available. And when you can do that for a physics situation or even a non-physics situation, then when you can write out an explicit mathematical formula for f of x equals blah, 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 function of x, for some like physical situation or whatever else you might come up with, then we call f the mathematical model of that situation. It could be a mathematical model of something about physics, could also be a mathematical model of something like population change with time, etc. And so the reason that we do things like that, where we represent things of interest to us with functions, is because we want to be able to understand them and make predictions. And so if a function is given by a formula, and the domain is not stated, explicitly, the convention is that the domain is the set of all numbers for which the formula makes sense and defines a real number. So for example, if we take g of x equals, it catches these like accidental marks. So g of x is equal to 1 over x times x minus 1. So division by 0 is not going to be allowed. So that means g of x is not defined. For x equals 0 or for x equals 1. And so the domain of g is going to be x such that x does not equal 0, and x does not equal 1. And we can write this in an interval notation. So just to remind people of this kind of notation, negative infinity to 0 open, meaning that it doesn't actually include 0, just every number up until 0. This is a union. So it's a union of sets here. So then the union with the set 0 to 1 open, and then the union with the set 1 to infinity open. All right, and then so a few more things about functions. So just so people remember the idea, there's a vertical line test can be used to test if function is a function. Remember that we're looking at calculus of single variables right now. So that means that we will have functions like f of x, where x is a real number, and then f of x is also a real number. So we'll be able to plot these and then look at these functions. So for example, if we make this plot, we can see that at every point, for example, here is the independent variable. For each value of the independent variable, there is exactly one value of the dependent variable for this function. So that one is a function. So it passes the vertical line test. This is as opposed to something like this one, where, as you can see here, for a single value of the independent variable, there are two values of the dependent variable. That's not allowed by our definition of a function. For this one, this plot does not represent a function. And so if we want to go back and say, oh, why is that? It's because a function f is a rule that assigns to each element x in a set exactly one element called f of x. So it can't assign two. That's why we're saying this one is assigning for an element in the domain, it's assigning two values in the range, not allowed for a function. So this one is not a function. Okay, there's some other things that just to jog people's memory. So piecewise defined functions. These have different formulas in different parts of their domain. So an example is actually absolute value. So if you take the absolute value of a number, it would be equal to a if a is greater than or equal to 0. And negative a if a is less than 0. This one threw me a bit when I first read that, but luckily that book is really good and it clarifies that when a is less than 0, then a is a negative number. So the negative of a negative number is positive. That's why the absolute value would still be positive here. That's the idea. So there's also step functions, which just suddenly change value. As an example of something like a step function that just suddenly jumps from one value to the next, we can have something like C of W is equal to 0.37 if 0 is less than W is less than or equal to 1, or 0.60 if 1 is less than W is less than or equal to 2. The book's example goes on and actually presents 4 different options, but that's sufficient for showing the idea. You can see that it jumps the value. So originally when W is in this range, so the independent variable is in the range 0 to 1, then the dependent variable's value is 0.37. Otherwise, when it's between 1 and 2, then now it's 0.6, so there's a steep jump in the value. Another set of terminologies that are helpful, just for everyone to know, is a function f is increasing on an interval I. If f of x1 is less than f of x2, whenever x1 is less than x2 in I, and it is called decreasing on I if f of x1 is greater than f of x2, whenever x1 is less than x2 in I. And so as an example of that, so f of x equals x squared is going to be decreasing on the interval negative infinity to 0. And then it's going to be increasing from 0 to infinity. Okay, so that covers a little bit about functions. A few more things is that we can start to put them in categories. So for example, if y is a linear function, of x, that means the graph of the function is a line. Something like y equals mx plus b. So the linear functions have their y grow at a constant rate. Polynomials are another type of function. So a function is a polynomial if you can write it like p of x is equal to a n x to the n plus a n minus 1 x to the n minus 1 plus dot 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 plus a2 x2 plus a1 x plus a0. So it has to be n, it needs to be non-negative integer. And these a0 to an are all called the coefficients of the polynomial. And if an is not 0, the degree of the polynomial is n. Hopefully people are paying attention to the way that we're writing these things. For example, an does not equal 0, the degree of the polynomial is n. This is a lot more in line with how we would write a technical paper, try to express things about mathematics. We would be very rigorous in defining what we mean and in defining terms and in defining them with respect to some type of notation. So then we also have power functions. So these have a form something like f of x equals x to the a, where the a is some type of constant. Then we also can have rational functions, which are ratios of two polynomials. We can have algebraic functions. And these are made by doing algebraic operations on polynomials. So for example, adding, subtracting, multiplying, dividing, taking roots for polynomials. So something like f of x equals root x squared plus 1. So you can see I took the square root here of a polynomial. That means this is now an algebraic function. There are the trig functions, which if you don't remember those, you can do a quick jog of your memory. Things like, for example, that sine of x plus 2 pi equals sine x and all kinds of properties. Exponential functions. Logarithmic functions. The inverse functions for the exponentials. And then transcendental functions. Those are the things like the trig, inverse trig, exponential, log, and a lot of unnamed stuff that are not algebraic. And then you can also combine functions. So you can add them, multiply them, etc. But also it's important to remember what we call the composition of functions. So that's things like f of g of x is equal to the composition of f and g. The order matters here. So for example, if you have y equals f of u equals root u, and then you have u equals g of x equals x squared plus 1, then you could say, oh, okay, well, y is actually a function of x then, because g is a function of x and y is because u is equal to some function of x, and then y is a function of u. So then you could always plug that in and you could say like, okay, well, if this is true, it's a function of g of x, which is equal to f of x squared plus 1 equals root of x squared plus 1. And so then this would be the composition. And so as you can see, if I was to flip the order and to do G first before F, then that would not be the same as this. So here, very specifically, argument of F is what G of X is. And then you plug that in. Okay, and just a little more stuff from the first chapter here. This is important for graduate students talking about writing proofs. So as undergraduates, generally proofs are kind of like, well, who cares about that except all the mathematicians? We just need to know how to use this for engineering. Well, in a graduate level class, I can say that you are going to have to understand things about proofs, because what's important at the graduate level is that I'm teaching you how to go through the literature. And I can say that at the graduate level, if you're really going to do mathematics, then a lot of what's going to happen in the literature for you is going to be proofs. Because if we were only ever just using the things that exist, then might not be too much research. So if we're actually going to be developing things involving mathematics and making new discoveries that involve mathematics, most likely you're going to have to write proofs. Or if you're not the one who's actually going to be making those discoveries, then what's going to happen is you're going to have to be able to understand the results of people who are making those discoveries, because you're going to want to be applying their work in new contexts or understanding how they did what they did, so that you can really be doing something in a rigorous fashion and making sure as a researcher that you're doing everything correctly and that you really understand why you're doing what you're doing and not just taking it for granted. And so that means that at some point as a researcher, you're probably going to have to be able to look at things in where people have written mathematics in some form and that they are proving something, or that you're going to have to prove something. So it's a good idea to understand how proofs are constructed and how to do them. And so there are many ways that we have to do these. When I first started in graduate school, my first class that I took there was an advanced electrical engineering linear algebra class. And I was like, whoa, I've never even learned how to prove things like this. My undergraduate was in chemical engineering, and we didn't talk about all these proofs with linear algebra all the time. And certainly even the ones that I did in linear algebra class were nowhere near as complex as these and difficult to see. And I thought that that was a big shock in graduate school and having to do all these proofs. And so what I think can help is being told a little bit about what is behind proofs. And then a lot of it, you just have to get used to it by doing a class like this one, where you're going to see proofs and then the idea of how people start to think at the research level about mathematics. So there's going to be things where you can try to think of a similar proof and build off of that one, if such a thing exists. Another thing is that you can find patterns occurring. So for example, you might realize as you're proving something that there seems to be a pattern. This happened to us somewhat recently in our group, for example, that we were saying, okay, here's what the error is on this term, and here's what the error is on the next term, and here's what the error is on the next term. And then we realized there was a pattern, so that we could actually write a general statement to say, okay, here's what the error is. And so patterns are great if you can see them. You a lot of times have to prove for all cases. We do this a lot, where when you want to prove something, there are actually many different scenarios. So for example, in our group, we have some things lately that we've been looking at with cyber attacks on control systems. And so then when we develop new controllers, we need to be able to demonstrate that our controller acts in a certain way without cyber attacks and then acts in a certain way with cyber attacks. And so we need to make separate proofs for each case. Then you can also do proofs by contradiction. This is a bit more sophisticated. So that would be a case where something like the following, it would need a bit more depth in the loose description I'm going to give here. But to prove that P implies Q, assume P is true and Q is false, and prove that's impossible so that Q has to be true. Now, that does mean some things about, for example, Q has to be able to, it has to be true that there's not like something where, there's like some loophole in the setup that you made for the proof by contradiction, but that's the main idea. And then this one also is one that we use a lot, proof by induction. So this would be, let Sn be a statement about the positive integer n. Suppose that S1 is true, Sk plus 1 is true, whenever Sk is true, then Sn is true for all positive integers n. So that's the idea of proof by induction, and that's also a really good one. Okay, so that covers the basics on functions and a little bit about background on proofs. And so now we're going to move into chapter 2. So this one is going to be about limits and rates of change. So way that we can motivate, one way to motivate limits is by thinking about tangents to a curve. And so let's draw this picture here. And so here we have x and here we have y, and this is y equals x squared. So here's my curve. And so I can take these points here. Let me call this one P and I'm going to call this one Q. So I want to get the tangent at P. So very specifically, I want to find an equation of the tangent line to the parabola y equals x squared at the point P 1, 1. So what that means is that that's where x is 1 and then y is 1. So that's the point. Point is 1, 1. So the hard part here is I only know one point on a line and I'm being asked what's the equation of the line. And so for people who are familiar with like y equals mx plus b, you know that if you don't know m and you don't know b and you only know a single point, you're not going to be able to get m and b from only a single point on the line. So then what can you do? So instead, well, maybe I can take a point Q that's nearby P, and I could instead try to get like a slope through these two. So maybe it's not exactly the same as the tangent. So the tangent through P would probably be more like, sorry, bad drawing, but something like this, but it's not that far off of the line for P. The closer and closer I bring Q to P, I will actually get more and more close to the actual tangent line. So what this means is that I can approximate the slope of the actual tangent line by choosing my nearby point Q, and point Q is going to be x squared. This is my x coordinate, and here's my y coordinate on the parabola, and then computing the slope of the line through P and Q. And as I move closer and closer and closer to P, I'm going to get my slope more and more aligned with the actual slope of the tangent. So for example, let's say that Q is not P. So then I have this MPQ, so the slope of the line through P and Q is equal to x squared minus 1. So this is y, which is x squared for Q, minus 1, which is a y for P, over x minus 1. So this is going to be the x for Q and the 1 for p. And so this is the slope of my secant line. And so as I take the points Q closer and closer to P, meaning that the X gets closer and closer to the 1, then it looks like as X goes to 1, if you were to actually plug in a lot of numbers, you would see this. So you can convince yourself if you're not sure what I mean. As X goes to 1, probably say, then MPQ seems to be going to 2. So this suggests that the slope of the tangent line is m is 2. And then, so the slope of the tangent line is the limit of the slopes of the secant lines, which we can write symbolically as limit as Q approaches P of MPQ equal to M, or because we said P has X equals 1, the limit as X goes to 1 of X squared minus 1 over X minus 1 equals 2. So as you can see here, limits come in a lot of cases where you're trying to make two things be close to each other. And so we want to talk about what is the actual definition of a limit. So in some type of less formal sense, we'll get a more formal definition of a limit later, but we write the limit as X goes to A of f of X equals L. So this is some notation that we're defining here. We write this, and this is notation, and we can say that this means the limit of f of X as X approaches A equals L. When we say that thing, or we write this if we can make the values of f of X arbitrarily close to L, meaning as close as we would like to L, by taking X to be sufficiently close to A on either side of A, but not equal to A. So this is somewhat rough. It's not super precise. You make the value of X as close as you want to A, but not equal to A. There's a sense of what this probably means, but it's not exactly mathematical in construction here, but this gives us a sense of what we're talking about. So when we use this notation, we mean that I'm making X closer and closer to A. I keep evaluating f of X, and as I make it closer and closer to A, it seems that on either side, or when I make it closer and closer to A on either side of A, I keep getting a number that seems to be approaching L. And so people also might write notation like f of X goes to L as X goes to A. There are different notations someone might use for the same idea. You don't need to care if f of X is defined when X is A, just how it is near A. So even, for example, you don't have to have any value defined for f of X at A. We only care about taking X sufficiently close to A, but not equal to A. So then there's also these things called one-sided limits. So a one-sided limit is going to be like this, for example. So here's the notation for one-sided limits. This is going to be a one-sided limit on the left. So the limit as X goes to A minus f of X equals L. So this is the left-hand limit of f of X as X approaches A. Or alternatively, you could say it's the limit of f of x as x approaches a from the left is equal to L. So this would be true if we can make the values of f of x arbitrarily close to L by taking x to be sufficiently close to A and x less than A. And you could do sort of the other way, do it on the right hand. So then you would write the limit as x goes to A plus of f of x is L, meaning the right hand limit of f of x as x approaches A, or that the limit of f of x as x approaches A from the right. If we can make the values of f of x arbitrarily close to L by taking x to be sufficiently close to A and x greater than A. So there is also this general statement about limits. So the limit as x goes to 0 of f of x equals L. Sorry, limit as x goes to A of f of x equals L if and only if limit as x goes to A from the left of f of x equals L, and the limit as x goes to A from the right of f of x equals L. So what this means is that if and only if means it has to go both ways. It means that if the limit as x goes to A of f of x is L, then the limit as x goes to A from the left equals L, and the limit as x goes to A from the right is L. Or if both of these are true, limits on the left and right are equal, and they're both equal to L, then the limit as x goes to A of f of x is L. So that's what this means. You can also have infinite limits when your limit does not actually exist. Then we can talk about the way in which it does not exist using infinity. So for example, let's take the limit as x goes to 0 of 1 over x squared. So in this case, if we make this plot, it will be like this. So here we have x and we have y, we have 0. And then, so the values of f of x as x is approaching 0 on the left and the right, they don't actually approach any number. They're actually going just increasing without bound. And so the limit as x goes to 0 of 1 over x squared does not exist. So this does not exist. But we can try to denote the particular manner in which it does not exist using the following notation. So this does not mean that the limit exists. This just means it doesn't exist in the sense that instead the left and the right hand limits are both increasing without bound as you approach 0. And so what this means is that 1 over x squared can be made as large as we like by taking x close enough to 0. And so just as an example of how we would write this definition, we would say let f be a function defined on both sides of A, except possibly at A itself. Then we've got that the limit as x goes to A of f of x is equal to infinity, means that the values of f of x can be made arbitrarily large by taking x sufficiently close to A, but not equal to A. you could imagine something similar for if it was actually going to be negative infinity. So they could be made as arbitrarily large negative as we want, taking x sufficiently close to a, but not equal to a. And so then there's also the definition of a vertical asymptote, which is related to all of these. So vertical asymptotes are when some of these limits on the left or the right, or just as x approaches a, are equal to infinity. So now that we have some things about limits here under our belt, let's talk about how do you actually calculate them. This is probably about where our heads were at when we first learned calculus. I don't know about you. I can certainly say this would have been the part that when I first took calculus, I would have felt like, forget all these definitions. How do I calculate these things? Or forget about any proofs or why these are true. How do I calculate this stuff? Because I need to know how to, get the right answer on my homework. But what we're going to see pretty soon is we're going to actually be able to prove one of these limits. And so all these other ones are going to be able to be proved in a similar way. And I think it's important at the graduate level to start thinking about proofs and why are these things true? Where are they coming from? And not just how do I calculate them? Relatively straightforward, I think, from our undergraduate education, know how to calculate them as long as someone jogged your memory on it. But remembering how to prove them and thinking about them from that deep level of why is everything true and how do I make sure I can really get it from the basics and that there's nothing, no uncrossed T or undotted I or whatever, that that's really important to think about at the graduate level. So I'm going to write out all the limit laws here. Later, we're going to prove one of these. And so let's say, suppose that C is a constant. And the limits that the limit as x goes to a of f of x and the limit x goes to a of g of x exist, then please do note, this is really important. Anytime you have a theorem, it's really important to note what the caveats are. Suppose these things are true, then this. Actually really important that you would have to verify these things were true before using these statements, not just to blindly use them. So this would say that the limit as x goes to a of f of x plus g of x equals the limit as x goes to a f of x plus the limit as x goes to a of g of x. We also have that the limit as x goes to a of f of x minus g of x equals the limit as x goes to a of f of x minus the limit as x goes to a of g of x, that the limit as x goes to a of c f of x, where c is that constant that's noted up here, c is a constant, equals the limit as x goes to a of f of x times the limit as x goes to a of g of x. Oh, sorry about that. I copied the wrong line from my thing. C limit x goes to a, that's for the next one, f of x. Sorry about that. And the limit as x goes to a of f of x times g of x, this is the one, it should be what I wrote above, equals the limit as x goes to a of f of x times the limit as x goes to a of g of x. And finally, that we have that the limit as x goes to a of f of x over g of x equals the limit as x goes to a of f of x over the limit as x goes to a of g of x if the limit as x goes to a of g of x is not 0. Again, caveats are very important. Okay, so let's do a quick example on the side here of actually using these limit laws. And like I said, later we'll get to the point that we can prove one. So here's an example. So the limit as x goes to -2 of f of x plus 5 g of x And let's say that we know what's true about the limits, this for f of x and g of x, because that's part of what's required for this theorem, is, or for the statement, I guess, that the limit as x goes to -2 of f of x, say it exists and it's actually equal to 1, and that the limit as x goes to -2 of g of x exists and is equal to -1. So then we're going to do, okay, I'm going to split up this limit. So the limit as x goes to -2, first I'm going to use this first point. So I'm going to say, okay, here's my first function is f of x. My second function here, one that they call g of x here, is actually 5g of x here, because this just means first function, second function. So here's the second function. So I'm going to split that up. So it's going to be f of x plus the limit as x goes to -2 of 5g of x. Now I'm going to come down here and I'm going to use this law with the constant. So in this law with the constant here, c is 5. And so I'm going to pull that out. This is equal to the limit as x goes to -2 of f of x plus 5 times the limit as x goes to -2 of g of x. Okay. And then finally, I can plug in these numbers now. So this one is equal to 1 plus 5 times, and then this one is equal to -1. So in total, this is -4. So that's probably about what people used to do. And so there's like a few more random ones that come out of those different things, but just to really write them quickly for completeness here. Here's one that you can get. There's some other things. So like limit as x goes to a of c equals c. That's an important limit. Another one is that the limit as x goes to a of x equals a. That the limit as x goes to a of x to the n equals a to the n, where n is a positive integer. And then if n is even, we do assume that the a is positive so that this doesn't, sorry, that's for the next one. The next one, the limit as x goes to a of root n of x equals root n of a, for n is a positive integer. This is the one where what I was just saying. For this one, if n is even, then we assume a is greater than 0, so this doesn't cause a problem taking an even root. So that'd be like a square root, for example, of a. You definitely need to make sure that in that case that the a is positive, or else this is undefined, so we kind of implicitly assume that. And then that the limit as x goes to a of root n f of x equals the limit brought inside of f of x. So again, n is a positive integer. And if n is even, we assume that this part that's in the brackets here is positive, or sorry, in the root is positive, so that, okay. And then there's this direct substitution. Property is for polynomials and rational functions, which are the ratios of polynomials. So if f is a polynomial or a rational function, and a is in the domain of f, then the limit as x goes to a of f of x equals f of a. So I used that one a lot when I took calculus the first time. And then something that I think is really interesting, again, this is sort of, all these things are interesting to me in hindsight, kind of knowing how much more I know now compared to what I knew the first time I took this class, and going through the same book again and being like, oh, wow, like I definitely missed the whys on a lot of things. There was a lot of things where I think I was doing them just because someone told me, well, that's like, look out for this sort of case and then do it that way. And I don't think I always understood why we were doing it that way. And so let's call this f of x. So in this, we can say, oh, okay, can I use all those limit rules from before? So for example, can I say that this is equal to the limit as x goes to a of f of x over the limit as x goes to a of g of x? Oh, sorry, the limit as x goes to a of some numerator over the limit as x goes to a of the denominator. So can I do it like the limit as x goes to 1 of this over the limit as x goes to 1 of this? And the answer is no, and the reason is because of this caveat here. This goes back to what I was saying, that you have to be really careful with your caveats. So this says, no, you cannot use this if the limit of what the function on the denominator is would be equal to 0. And then so here, if I take the limit as x goes to 1 of the polynomial in the denominator, it's going to be 0. Therefore, I cannot use functions, therefore I cannot use this property right now. But instead, I could say, okay, well, but this function is equal to another function. So f of x here, this total thing, numerator and denominator, is factorable. So then I can cancel these out, and I can say it's equal to x plus 1. And let me call this function g of x. So these two functions are equal everywhere, but at x equals 1. Because these two functions are equal everywhere, but at x equals 1. G of x and f of x. F of x equals g of x, except at x equals 1. And so from the perspective, though, of taking the limit as x goes to 1, remember that when we're taking limits, we don't actually care about the value of the function at the point that we're taking the limit at. We only care about getting arbitrarily close, but not equal. So the fact that these two functions are the same at every point except the point that we don't care about means that it is super fine for me to look at the limit of g of x to give me the limit of f of x as x goes to 1. So in general, if f of x is equal to g of x when x does not equal a, then the limit as x goes to a of f of x equals the limit as x goes to a of g of x. And so some limits, it's the best to calculate them by finding the left and the right hand limits, where you need to check on the left and you need to check on the right and you need to check that they're equal, and then you set that equal to the limit, and that's going back to the statement here. So if you were to calculate this one and you were to calculate this one, then if they are equal, then they are equal to the limit as x goes to a. For example, that could be one way to calculate the limits. These are all ways of calculating the limits, but a lot of what we do a lot of times in actual research is we don't sit around calculating most of our numbers when we're making new proofs. We will instead do them in some general form where we will prove something general and not necessarily like a solid number. But then, okay, and then so two other important theorems for limits are going to be this one that says if f of x is less than or equal to g of x when x is near a, except possibly at a. And the limits of f and g both exist as x approaches a, then the limit as x goes to a of f of x is equal to the limit as x goes to a of g of x. And then there's the Squeeze theorem, which is also important. So this one says that if f of x is equal to g of x, then equal to h of x when x is near a, except possibly at a. And the limit as x goes to a of f of x equal to the limit as x goes to a, h of x is equal to L. then the limit as x goes to a of g of x with L. So what these last two say is this is a statement about if the value of one function evaluated at all the x's near a except possibly at a is always less than or equal to the value of another function evaluated at all points x near a but possibly not at a, and then the limits of both functions exist as x approaches a, then you can tell something about which of the limits is actually greater. And then this one is about how you can tell what the limit of this function g of x is from looking at limits of two functions that bound that function. And so, so that's good. So now though, let's get to the precise definition of a limit. So this is going to be a little more intense, and this is going to get to a little more on how I typically like to think in mathematics. So the precise definition of a limit, where we start to get to the point that we can actually prove things and write things in a rigorous and mathematical sense. Okay, so before we had a number of things that we've talked about. So just kind of going back through our slides, if we go to right here, we are reminded that our thoughts about limits were motivated in many ways in this discussion by saying, oh, well, what if we take the secant line here and we get the secant line closer and closer to the tangent line, then the limit of the secant line's slopes is eventually going to give us the tangent line slope. And then that sense of saying, oh, if something gets close, if my dependent variable gets close to a number equal to that number, and I look at what the dependent variable is doing, I can get a sense of what my limits would be. And then we were able to use that and say, oh, by the way, here's some things that are true about limits. Maybe you don't exactly know why these are true yet, but just believe me. We kind of wrote a lot of things. But now we're going to get to the point where we say, okay, what is rigorously true? Not just this, it gets really close, or oh, these statements about limits are true. We could intuitively see a lot of those things, but now we're actually going to talk about why is it mathematically. We want to do better than what we've been doing. So this is where we start getting a lot more like how we talk in papers that involve like first order ordinary differential equations. We'll often talk a lot more in the kind of language that I'm going to start presenting in the end of this lecture for this part of the chapter. So it's good to get familiar with the way that math is kind of written in research. So here it says, let f be a function defined on some open interval. Now, because we're dealing with functions of a single variable still, that would be something like 0 to 2. So you can see here, the parentheses are open. So it's an open interval because it's not closed. It doesn't include the boundaries. It doesn't include 0 and 2. It's every point up to that. So let f be a function defined on some open interval that contains the number a, except possibly at a itself. Then we say that the limit of f of x as x approaches a and we write that the limit as x goes to a of f of x equals L if for every epsilon greater than 0, which is a positive number, there exists, that's what this symbol means, this backwards kind of E looking thing. There exists delta greater than 0, which is another positive number, such that, so ST such that f of x minus L is less than epsilon whenever 0 is less than x minus a is less than delta. You could also say this last part such that if 0 is less than x minus a is less than delta, then f of x minus L is less than epsilon. So remember that this is still functions of a single variable. So the symbol here means absolute value. And then, so the idea of this is that no matter how close I want to get f of x to L, so for any epsilon, no matter how small this epsilon is, however close I want to get to L, but not equal. So as you can see, it has to be less than epsilon, and epsilon is greater than 0. So it's not that f of x is equal to L, it's just that it is arbitrarily close. Then it can get as close as I want by me choosing the right difference between x and a. So I can make x closer and closer and closer to a, and as I do that, at some point, I get f of x to be within L. And so if that's true for any epsilon and delta, then we can say that the limit as x goes to a of f x is L. So if this is not something that you paid attention to the first time when you learned calculus, or that you didn't go over because it starts to get into more of the language that is a little more hard to understand, then now is your great chance. So there are ways we can frame this. So we can say the limit as x goes to a of f of x equals L means that the distance between f of x and L can be made arbitrarily small, taking the distance from x to a sufficiently small, but not 0. There's a lot of other ways you could kind of write this and say this, but let's try to visualize this to start getting some intuition about what we mean. And so let's see a sort of example here. So let's take f of x equals 2, I'm going to define this like this, 2x minus 1, if x is not 3, and it's going to be equal to 6 if x is equal to 3. So this is just a line on my x, y axes. And so here is 3. And so here is what the point on the line is when on this line 2x minus 1 if x is 3, but that's not the value of this function f of x. When x is 3, it's actually going to be 6. So, so you can see that if this was on the line, at this point on the line would be 2 times 3 minus 1 equals 5. So the point here is 5. Then my actual function's value is up here. It's at 6 because there's this hole right here, according to this. So then let me then also define these kind of range around 3. So you can see here, here's delta and here's delta. So over here, this point, ding, ding, is going to be 3 minus delta, and this point over here is going to be 3 plus delta. So we're saying that we are going to have our x in here. So when x is in here, so it's between 3 minus delta and 3 plus delta. Then up here, we have 5 plus epsilon and 5 minus epsilon. So when x is in this range, then f of x is in this range. And so that's the idea about that. Then if I make this, if I say, oh, okay, I want it to actually be, you know, really, really close to 5, and that means I have to be able to find these deltas that make sure that even if that means I'm a little more constricted around 3, that I still am able to get whatever epsilon I need. So this might also make a little more sense if we write out something. So the distance from x to 3 is x minus 3. And the distance from f of x to 5 is f of x minus 5. So what we want to do is we want to find delta such that f of x minus 5 is less than some epsilon if x minus 3 is less than delta that x does not equal 3. So right now, let me go back up. So that's following this. So we're saying that the limit of f of x as x approaches a is L if every time that we get x minus a less than some delta, exists some delta such that I can get x minus a less than that delta, will give me that f of x minus L is less than epsilon. So over here, I want to say, oh, okay, I'm going to get x minus 3 less than some delta, and that will give me f of x minus 5 is less than some epsilon. And so that's because the limit, it looks like in our graph, it's 5, and that's for 3. The reason that we think it looks like it's 5 is because we can see here this number 5 was right where the discontinuity is, but everywhere else around it, it appears to be heading toward 5. So this is what we want to demonstrate. We want to show that the 5 is the limit. And so the way to show that 5 is the limit, according to the rigorous definition we just said, is to demonstrate that this is true. Find a delta such that I can always be within epsilon. And this has to hold for all epsilons I come up with. So let's say I start by saying, say epsilon is equal to 0.1. Someone says, okay, I want you to be within 0.1 of 5. Well, then I can say, oh, okay, let me see if I can. So I'm trying to find f of x minus 5 is less than 0.1 if x minus 3 is less than delta, but not 0. So let's take an educated guess here. So we could say, hey, look, if 0 is less than x minus 3 is less than 0.1 divided by 2 equals 0.05, then what I get is that f of x minus 5, I'm going to plug in the function f of x. So it's this everywhere except x is 3, and that's the points I care about right now. I don't want to look at when x is 3. I want to look at when x is not 3. But when x is not 3, I'm going to plug in this part, 2x minus 1. So it's 2x minus 1 minus 5 is equal to 2x minus 6, which is equal to 2 times x minus 3. And I want this ideally to be less than 0.1. So what this looks like is I could also rewrite that last statement as x minus 3 needs to be less than 0.1 divided by 2 equals 0.05. So it looks like if I choose my delta to be 0.05, then I show that x minus 3 is less than 0.05, gives me that f of x minus 5 will be less than 0.1. So that's great. I proved that much. So I demonstrated that there exists a delta if epsilon is equal to 0.1, such that x minus 3 less than that delta, then f of x minus 5 is less than the epsilon. To prove that 5 is really a limit, I would have to demonstrate that this was true no matter what epsilon I have. So even if I make epsilon 0.01, even if I make it 0.001, always has to exist some delta. Now that delta might need to get smaller. It's not going to be 0.05 anymore. It's going to be smaller than 0.05 if, for example, epsilon was 0.01, but there has to exist some delta. And so then we say, well, can I make that general statement here? Well, it turns out that yes, that if I do f of x minus 5 is less than epsilon here, if 0 is less than x minus 3 is less than delta equals epsilon over 2. And so you could actually demonstrate that this is a much more precise way than what we did at the beginning of this lecture, for being able to say what the meaning of a limit is. So it makes precise the notion that as you get close, so as your independent variable gets close to a certain number, then the dependent variable is getting close to another number. And it makes that idea precise here and allows you to actually be able to prove it. And this concept is what we call a challenge and answer form. So it's like I challenge you with some epsilon. Can you find a delta if the epsilon is this? And then someone tries to meet your challenge to find that delta. If they can always meet your challenge, then the number you have here is the limit. Okay, so we can do that again with one more example just to give the idea. So prove that the limit as x goes to 3 of 4x minus 5 is equal to 7. So we're going to translate that into math speak. So rigorously, we want to find, someone says prove this, we have to say, what do they mean? What do we need to actually prove? So we need to find delta such that for every epsilon greater than 0, for x, or I guess I should say for epsilon greater than 0, but for any of the epsilons. So for every epsilon delta, every epsilon there will exist a delta, but it's not necessarily the same delta for all the epsilon. So that this, if this is the limit is 7, then that needs to be the difference between 4x minus 5 minus the limit, which is needs to be less than epsilon whenever 0 is less than x minus 3 is less than delta. So we can notice that 4x minus 5 minus 7 is 4x minus 12, which is equal to 4 times x minus 3. So this means that 4x minus 3 needs to be less than epsilon whenever 0 is less than x minus 3 is less than delta. So it looks like we should be using here epsilon over 4. So let's say take delta equals epsilon over 4. Then given epsilon greater than 0, choose delta equals epsilon over 4. If 0 is less than x minus 3 is less than delta, then 4x minus 5 minus 7 equals 4x minus 12 equals 4 times x minus 3 is less than 4 delta, which if delta is epsilon over 4, would be 4 times epsilon over 4 equals epsilon. So we just demonstrated that it's less than epsilon. So this shows that 4x minus 5 minus 7 is less than epsilon whenever 0 is less than x minus 3 is less than delta. So by the definition of a limit that we said in this chapter, this means that x goes to 3 of 4x minus 5 must equal 7, because we were able to demonstrate that 7 met the definition of the limit, the epsilon delta definition of the limit. And so it's also possible to rewrite all the prior definitions that we had in this sort of rigorous form. So for example, definitions of the left-hand limit and the right-hand limit and the infinite limit. And so really quick, I'm going to write these out. So definition of the left-hand limit. So this one is going to be that the limit x goes to a minus of f of x equals L if for all epsilon greater than 0, there exists a delta greater than 0 such that f of x minus L is less than epsilon whenever a minus delta is less than x is less than a. You can imagine there's an analogous one for the right-handed limit, where the difference is going to be that a is less than x is less than a plus delta. There's also going to be the infinite limits, so let f be a function defined on some open interval. That contains a, except possibly at a itself. Then we have that the limit as x goes to a of f of x equals to infinity means that for every positive number m, there is a positive number delta. such that f of x is greater than m whenever 0 is less than x minus a is less than delta. And then there's kind of an analogous one for the limit at negative infinity, where it'll be f of x less than a number that's negative. Notice this, that this one is a little different. So it says f is a function defined on some open interval that contains a except possibly at a. You're getting the infinite limit if for every number that you can imagine, no matter how big it gets, you can always find a number close to a. You can always find an x close to a that will cause you to have your function f of x exceed that number, no matter how big it is. Okay, and then so I wanted to make one caveat, and then we'll do one last proof. But one caveat about this slide is that I think that this kind of implies that, oh, wow, like how would I ever, how often is it that limits just work out so nicely like that it's just so obvious how to do the proof? I would say, like, I don't think that this is representative of things that happen in general. And I also kind of, like I hinted at earlier, I think it would be relatively rare that you would make proofs in actual like research papers starting from actual numbers. Like usually it will be much more similar to what I'm about to do, where you're still working at the level of generality of you just have functions like f of x and g of x, you're not actually plugging them in. I would say it is probably relatively rare that you would actually be in a situation outside of maybe like a toy problem for class, where you would actually be finding the actual numbers that are associated with limits, substituting for f of x an actual function and then saying, oh, look, you can see this relationship. It'll be much more general, I think, most of the time, at least in what I've done with proofs. So no, they are not always that obvious. No, they are not always that simple. And one definitely was made to showcase the concept and to be simple enough that it worked out. But even in cases when you don't know the actual functions, like we're going to show here, this is the proof of the sum law, actually can still prove a lot of things. And so I think this is much more representative of the way that a proof would go in the literature. I mean, as representative as you can be in single variable, like calculus. I mean, this is not really where the literature is at these days. It's not really doing much single variable stuff in chemical engineering, but I think that this at least will give you some better sense. So if we go back, remember that the sum law is a statement that has some caveats and says if these are true, then. So it says suppose the limits of the limit as x goes to a of f of x and the limit as x goes to a of g of x exist, then the limit as x goes to a of f of x plus g of x equals the limit as x goes to a of f of x plus the limit as x goes to a of g of x. Okay, so proof of this, that's what we're looking at. And it's going to take advantage of the definition of a limit. And like I say, this is much more moving toward the type of thinking people really have to do when they're writing proofs and papers. So this uses triangle inequality. So let me just introduce that up here really quick. I'm writing triangle. Triangle inequality. So this is going to say that a plus b is less than or equal to a plus b. So the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. This is an important inequality even when you get to vectors, where you will use it for norms, but let's not worry about that right now. We're just talking single variable calculus. So let epsilon greater than 0 be given. So remember, we're talking our challenge and answer form. Someone challenges you with a given epsilon. They say it's greater than 0, but here it is. So when that's true and someone gives me a challenge, so we must find delta greater than 0 such that f of x plus g of x minus L plus M. I should have stated that this limit is equal to L and this limit is equal to M. That also doesn't look like an M right there. M. Is equal to f of x minus L plus g of x minus M. Let's stop here for 1 second. So how did I know to write it this way? Well, because I think it's good to think of it that you want your first step to be to write what you're trying to prove in mathematical terms. So it's saying, okay, suppose that this limit is L, this limit is M, then prove that the limit as x goes to a of f of x plus g of x equals the limit as x goes to a of f of x plus the limit as x goes to a of g of x. So in order to demonstrate that, I'm going to use the definition of the limit. So I say, okay, what would it mean if this was true? So what it would mean is it would mean that f of x, that given an epsilon, there needs to be a delta such that, and then I have to write the two halves. So the first half of the definition of the limits is to write the part where you say f of x minus L is less than epsilon, and then the next part is say whenever 0 is less than x minus a is less than delta. So right now I'm writing this part, the f of x minus L is less than epsilon. So the f of x here means the part that I'm getting the limit of. So okay, here's the part I'm getting the limit of, and then I have to minus the limit. So the limit is going to be the sum of these two because I'm claiming that that's what this would be, right? So if these are the limits of the two, and if this statement was true, this part would be equal to L and this part would be equal to M. So it's saying that the limit as x goes to a of f of x plus g of x is equal to L plus M. So I would need to prove that that is the limit. So here then I would treat it as saying, okay, so here's the function I'm getting the limit of minus the limit. And then I'm just splitting these terms up a little within the absolute value sign, that's fine. Is less than or equal to f of x minus L, this is using the triangle inequality, plus g of x minus M. I need to find a delta such that this thing is less than epsilon whenever 0 is less than x minus a is less than delta. I should have actually written this part up here. So this is what I want to prove. And then I note that from this step to this step, this statement here, excluding this epsilon, but this statement, f of x minus L plus g of x minus M absolute value is less than or equal to the absolute value of f of x minus L plus the absolute value of g of x minus M. So then what we get is that we could make f of x plus g of x minus L plus M less than epsilon, which is our goal here, trying to find a delta such that this is true. We could do this if f of x minus L was less than epsilon over 2 and g of x minus M was less than epsilon over 2 whenever this statement over here was true. Because then when we sum them up over here, if we say, oh, that's less than epsilon, oh, okay, then we have an upper bound. So let's try to see if that could work out. So we're going to say, since epsilon over 2 is greater than 0, and the limit as x goes to 0, f of x is equal to L, there exists a delta 1 greater than 0 such that f of x minus L is less than epsilon over 2 whenever 0 is less than x minus a is less than delta 1. And then we also will have that a similar thing for the other case. So since the limit as x goes to a of g of x equals M, there exists delta 2 greater than 0 such that g of x minus m is less than epsilon over 2 whenever 0 is less than x minus a less than delta 2. So let's say that we take the minimum, say minimum of delta 1 and delta 2. So we take the smaller of the two. Then we know that if 0 is less than x minus a is less than delta, then 0 is less than x minus a is less than delta 1, and 0 is less than x minus a is less than delta 2. So f of x minus L is less than epsilon over 2, and g of x minus m is less than epsilon over 2. And then we have what we wanted over here. So we get that these parts are both less than epsilon over 2. So their sum is less than or equal to epsilon over 2 plus epsilon over 2 is less than, or which is equal to epsilon. Oh, sorry, I should have made this a strict inequality because both of these are strictly less than epsilon over 2. So now we have demonstrated that f of x plus g of x minus L plus m is less than epsilon whenever we have the 0 is less than x minus a is less than delta. So we've demonstrated that by the definition of the limit, that this means that the limit as x goes to a of f of x plus g of x equals L plus m. That's pretty cool. So that's, as I said, that's a demonstration in many ways of this principle. And so I'm going to stop recording this and thank you all for coming.